Welcome to the first Science on Tap for fall 2021. We are glad that you all could be here to join us for this event. These are Science on Tap events. These are events where members from the community can come and explore the latest ideas in science and technology that are occurring here at Cal Poly Pomona. Our goal of holding these events are to bring scientists from Cal Poly Pomona out of the lab and the classroom and into the community, and to have a dialogue over drinks or dinner. Usually we hold these events at Innovation Brewworks here at Cal Poly Pomona, but we've been holding them virtually due to the pandemic. But we are hoping that in the spring we'll be able to hold these events live again at Innovation Brewworks. So stay tuned for more information about that. Before we begin, I just want to let you know that we will be holding another Science on Tap event on November 15th. Here we have invited Dr. Sigdell to give a talk entitled Poking Membranes with Sharp Needles. So if you're interested, definitely keep an eye out for the advertisements for that event as well. Also, we'd like to thank the Dean's Office, particularly Daniel Griggs, who is the Communications Events Coordinator. He puts together all the advertisements, the posters for this event, and does a lot of our advertising and media. We're really appreciative of him. We also want to thank all of the speakers that we've had and Dr. Risk today, who volunteer their time and effort and to come out to these and give talks. And of course, we want to thank you all for showing up and supporting. It means a lot that you come and you show your support and you be here. And so with that, I encourage you to grab your age-appropriate drinks of choice, and then we'll give a cheers to all those who helped with these events. So cheers. And on that note, I'm going to introduce our speaker. Generally what we do is you can ask questions and just put them in the chat, and then me or the other host will break in and ask those questions to the speaker. But at the end of the presentation, we will turn the time over to you and you can chime in, unmute yourself, and ask the question directly to the speaker. So tonight we have Dr. Jimmy Risk, who's going to be speaking about how random was that, and how random functions can be used to model or predict uncertain events. If I have that correctly, I will let him explain the modeling and the things that he'll be talking about today. Dr. Risk is an assistant professor here at Cal Poly Pomona in the Department of Mathematics and Statistics. He received his PhD from the University of California, Santa Barbara, in Statistics and Applied Probability. Before that, he got his bachelor's degree at the University of Michigan, Michigan State University. I don't want to get that wrong. He also did some time in France at the University of Lyon. And he joined Cal Poly Pomona in 2017, and where he's been an assistant professor. And since then, he's had many lectures, invited lectures, many presentations where he's been asked to give a presentation. And he's been very effectual in giving a lot of teaching experiences. And so with that, I'm going to turn the time over to him and we'll go from there.
Okay, thanks, Doug, for the intro. So yeah, I'm Jimmy Risk. It says James Risk here, but that's my birth name. I just usually go by Jimmy. So this talk, or this outline right here, kind of outlines the talk. So random function, we'll kind of talk about exactly what that means. It could mean a couple of different things depending on your perspective. And then this last bullet point here, talking about these details, I think the one that's most interesting, I'm going to try to spend a lot of time on it, is this super resolution project, because I actually did this with a master's student of mine who graduated this summer. His name is Charles Amelin. And we did something that was really, really cool, I think, about trying to understand this very technical thing and applying it in a pretty interpretable context, I think. So yeah, let me go ahead and get started. Just to get started here, like first off, what is a function? So a function, simply speaking, it takes an input and it gives a single output. So there's some very simple examples you can think about. So here's like age. Okay, so every time you have a birthday, your age gets increased by 1. So you plug in age, you get age plus 1, right? You're 35, your birthday happens, now you're 36. There's more complicated types of functions, like here's a mathematical function, the sine function produces a sine wave. But you can have functions of all sorts of things, right? So if you're having a haircut, you plug in messy hair, you get a clean head afterward, okay? So this is the idea of a function, just takes in an input and it gives you an output. So just as an example, we can think here, say we have a tree that grows 20 centimeters every year. So the height is related to its age by this function, right? So year 1, it'll be 20 centimeters, year 2, it'll be 40 centimeters. Now, is the above function realistic? It depends on what lens you're viewing this from. So as a very simple model, this might be a reasonable model, okay? But this is obviously not like 100% correct. Right? Trees, they will stop growing, or eventually they'll die away, and it's probably also not this like fixed linear growth. So we're going to kind of talk about what it means to understand a function like this, and how would we maybe create like a better way to model the tree's height. So the way to do this in statistical modeling, and I'll comment on this footnote in a second, but what it does is it adds an error term. Okay, so you can further like decompose this error term, but it represents basically error. Okay, so it's pretty self-explanatory. Now this could be measurement error, it could be model inaccuracy. It could also be just some error that you can't actually do anything about. Okay, so we'll talk about what that means also later. It's a catch-all term. Okay, so not all models can reduce this, but a good model, if we have enough data, will reduce it like as much as we can with that data. So as an example, let's think about if we want to flip a coin like 10 times, right? I say, okay, here's your coin, flip it 10 times. How many heads are we going to get? Well, there's some randomness involved, and there's randomness that you can't do anything about. You can't predict how many coins or how many heads there are going to be exactly. Okay, it's going to be some number between 0 and 10 heads, and you can say, well, I expect to get 5 heads. That's the average number if I repeated the experiment many times. But we can't think of this as a plug-in of you plug in the number of flips and you get the exact number of heads that will happen. Okay, so you can think of that as being like an error term in a sense, if you're viewing this from like a prediction perspective, because you can't predict the exact number of heads that would happen. Okay, so a good statistical model will reduce the predictable error and it will leave the irreducible error. So in this example, like you can't actually, you can't predict the number of heads exactly. Okay, so we want to leave some irreducible error. Otherwise, we get into this realm called overfitting, which is like you start fitting to some error that you shouldn't be fitting to. And I'll show an example of what that looks like. Now, in terms of this footnote, the term machine learning is, it's kind of vaguely defined. So depending on what field you're looking at, machine learning, like it means something to like the CS community, computer science. It might mean something different to a stats community. So I put this here because machine learning and statistical modeling, from the perspective of this talk, they're basically the same thing, which has to do with you have some sort of data and you're trying to create a model from that data. So it's a very broad idea and you can dive into different aspects of it. But essentially both of these ideas are covered in this talk. So in terms of like a complex data set, this is actually a pretty mild data set. Oh, and I forgot, this should actually be 6 because I forgot I changed the data set. But here's just an example of a data set where we have some fuel economy data. Okay, so again, this should be 6, but we have these 6 different variables. And we have the data for 234 cars. So you can just imagine you have some big table like an Excel sheet, there's 234 rows, and then you have these 6 columns. Now, one thing you could try to do with this data set is say, well, how can I predict the miles per gallon for a certain car? Okay, in that case, it would be an input of all of these different possible pieces of data, right? So how many cylinders does a car have? What is its horsepower? How much does it weigh, and so forth? And you can think like these 5 variables that are not miles per gallon, those aren't going to be able to perfectly predict miles per gallon, right? If you just add like a big old like cinder block to the back of the car, none of these are going to change. Well, I guess the weight will change, but I guess the point I'm trying to make is that there's going to be some other things that affect the miles per gallon, right? Are you recording it on highway or city driving, stuff like that? So essentially, we would want like a plus error term here to represent that sort of error that we can't actually account for with this data set. Would we use more data if we had it? Yeah, in a practical setting. But we're kind of viewing this from the point like, this is the data set we have. What can we do with it? So let's, I'll go back to that data set later, but let's talk about different types of statistical models, okay? So the simplest one is a linear regression model, okay? And this assumes a linear relationship. So what this means is that if you just think of like a line, right? You have your line, like you have your XY axis and you have your line. It has some intercept and it has some slope. So as X increases, the Y value increases along that line. Now we have an added complication because there's 5 different inputs. Okay, so essentially what we're looking at then is that there's 5 different coefficients. So we're not actually dealing with a line anymore, but we're dealing with what we would call a hyperplane. So that's the extension of a line into many dimensions. So you can think like, for example, if you're trying to imagine a line in 2 dimensions, it's like a plane, right? It's like a sheet of paper or something. Here's your line in 2 dimensions. That's a plane, but in higher dimensions, we call it a hyperplane. Now these coefficients here, they're fitted from the data, and I'll explain what that means in a minute, but it produces a line of best fit. Then you would use that line for prediction purposes. So this is basic. You would learn about this in like an intro stats course. There's a lot of theory behind it, but in order to apply it, you don't really need to know very much. Now, any assumption of randomness is placed on this error term. Okay, so this would be like, maybe errors due to measurement or maybe variables we haven't considered. You would just treat those as like random. So I just want to give an example of another one, which would be a regression spline. This one inherently, it doesn't need a random component, but what it does is it's a similar type of model, except it's a little more flexible. Okay, so I have something on the next slide here, which shows you a regression spline in just one. So there's one input. So you can think here is X on the X-axis and then Y on the Y-axis. And here are some data points in this spline. See, it looks smooth, right? It's kind of like wiggly. You can imagine the difference between like cooked spaghetti and uncooked spaghetti. So here is your cooked spaghetti, right? It's allowed to like bend, whereas a strictly linear model would just be a line. Okay, but a regression spline is just a model that does this. Now, very common in like the computer science community right now is something called a neural network, and you may have heard of this. It was originally designed to mimic how the brain handles information, and it's comprised of tons and tons of parameters. So if you want to look at this picture to try to understand it, this collection of green things in the middle, this is called a hidden layer. You can actually create multiple hidden layers if you want. So if you just like went online and grabbed some code to fit a neural network, you could have like 100 hidden layers if you wanted. Is that going to do a good job? Who knows? You have to be a real expert in understanding how to tweak these models to get them to work well. There's also a number of neurons per layer. So in this case, there's 6 of them. And this could be increased or decreased. If you want to understand this from the perspective of that last example, you would actually have 5 of these blue bubbles, and these all represent the inputs, right? So this would be like weight, number of cylinders, etc. So you're viewing it as this like complicated process where these all get plugged into each of these neurons, in which case there's a final calculation that produces what we would expect the miles per gallon of this car to be. Sometimes this is called like a black box type model because we don't really know, we don't have like a nice closed form understanding of what is going on in the middle. There are mathematical expressions for it, but it's much harder to analyze than, for example, this model right here. You can see very clearly as to what's happening, as cylinder changes or something like that. Whereas in this case, it's not nearly as clear, especially when all of these hidden layers and neurons are changing. Now, this is an incredibly powerful model. So a lot of like any sort of AI algorithms that you may know about, ones that like play Go or chess, or there are AIs that are like playing video games and stuff now. Most of their, I guess I shouldn't say most of, because I'm not an expert in this, but I know a lot of the techniques that are used in those are related to a neural network like this. Now, the Gaussian process, which is the one I'm going to focus on today, because this is what my research is based off of, this may appear complicated on the surface, and it's complicated mathematically, but it actually has some very rich properties that are pretty, they're very interpretable if you understand what's going on. That originated as a probabilistic concept as early as 1920. So if you ever heard of Brownian motion, that is an example of a Gaussian process. There's this botanist Brown who like observed this particle moving in like a petri dish. That's where this came from. Now, this is where the term random function comes from, because if we look at linear regression, which I talked about before, it was this linear form of the input, which you can see here. And the randomness came from this error term that we tacked on at the end. Okay, but this is completely deterministic. So this would be fitted from the data, like a line of best fit, which I'm going to show in a second. But the error comes from just adding this error term on there. So there's other ways we could throw an error term in there, but ultimately there's some deterministic component and then an error component. What a Gaussian process does is it actually assumes the function itself is random. And I'll explain what that means through some pictures to try to help you understand. But comparing to this, we always know that this is the form of this function. With a Gaussian process, we don't actually know what the function looks like exactly. In fact, we can get random functions. So you would get an entire plot of a function. We call this a sample path or trajectory, in which case, the functions are just going to look different every time you repeat this like hypothetical experiment. Now the functions, they're not like purely random. It's not just like some random mess. We put some restraints on the function by adding some different properties. So I'm trying not to go into that too much because I know there's a couple of slides dedicated to it, but we'll come back to this.
Dr. Risk,
Yeah.
We actually have a really good question in the chat related to the neural networks.
Uh-huh.
Can the neural networks handle discontinuities in the input parameters? So if we were looking at like that car data you were sharing, what would happen if you had, say, an electric vehicle that didn't have a cylinder? How can the neural networks cope with that kind of curveball?
Yeah, so I think I'm honestly not an expert at neural networks, but I know that a linear regression model, whoops, I'm going forwards. I know that a linear regression model like this can actually handle that. What you would do is you would add this thing called an indicator term, which essentially you multiply this by 1 or 0, corresponding to whether it's an electric vehicle. in which case this variable, this coefficient kind of like turns on if it's not an electric vehicle. And then you would add this additional term, which turns on if it is an electric vehicle. So at that point, it becomes like a branching model where you say, is it electric or is it not electric? And in which case it would do a prediction in either case, but it uses all of the data to fit these coefficients. Yeah, so it would be a nominal or categorical input. But it's converted to like a 1-0 variable, numeric variable, 1 if it's electric, 0 if it's not. I bring up the linear regression standpoint because this is the most common model. I would be astonished if a neural network would not be able to do this, and a linear regression model could. In fact, you could probably just construct like a trivial neural network that is actually a linear regression model in disguise and get it to work.
Thank you so much.
Okay, so let's go to like a tangible example here. So say we do have some data and we're going to ignore other variables. So let's say all we have is weight and miles per gallon. So here is some data. This is actual data from 1970 to 1982. And say that we're going to manufacture a new car with a weight of 550. So 550 pounds. What would the best guess for miles per gallon be? So essentially, as a modeler, you look at this data set and you say like, well, what is appropriate here? If you're wanting to pick out a type of model that looks like it would work well, you basically guess in some sense what type of shape this is representing. Okay, let's not get too far into that for now. Let's just, I mean, just real quick, if you wanted to produce like a guess, you know, I would probably pick somewhere around here. So it looks like maybe 10 miles per gallon. But let's just like stick to the basics, okay? So the first thing we could do is fit a linear regression model, okay? So what this does is it assumes that miles per gallon is a linear function, like I said here. So an intercept plus a slope times the pounds plus some error. So this is the line of best fit. Okay, so like I said right here, this portion right here is the deterministic portion. And then there's some error because obviously the line isn't going to fit to every single one of those points. So if we overlay this, it seems to do a decent job. So the red in red here, the red line is that line that we fitted. And then all I do is I plug 550 into this equation here. I do some simplification, like plug it into your calculator, you get 4.42. So this red triangle down here is what the predicted miles per gallon would be. Now, I did mention that we would talk about how this would be chosen. Like why would this line specifically be this line? Well, commonly the line is chosen to mathematically minimize the sum of squared distances to the points. So just as an example, like if you just imagine this line on your screen, imagine that the line gets just pushed up, right? You can imagine that it's going to be closer to some points, but a lot of those points, like at the bottom of this moon shape, they're going to be much farther. Okay. Also, if I change the slope, you're going to get a similar type of thing going on where our error would like increase because it's going to be further away from some points, even though it's closer to some points. Now, you might look at this and say, well, you know, this isn't very good. It's doing a decent job. Can we do better? And here's one issue with this model. What happens if I'm trying to predict a car whose weight is like 6,000 or 7,000? You get a negative miles per gallon. So there's a very clear like issue with this model. Is this model doing a decent job for cars that are between 2,000 to 5,000? Sure, depending on what you mean by decent. But we see that it's very obviously not working at higher values of pounds. So there's two things that went wrong here. One is we extrapolated. So in general, extrapolating is dangerous. So I just put the dictionary definition of extrapolate here, which says to extend the application to an unknown situation by assuming that existing trends will continue or similar methods will be applicable. So essentially, if you're thinking from a data standpoint like this, extrapolating is just doing something that is like not in your sample data. So we can see that by trying to provide a prediction of say 7,000 pounds, it's not even close to the highest weight car that I had. And I only have a few scattered car weights there. So this is extrapolating very, very heavy, okay? In general, we're not very good at extrapolating. It's hard to extrapolate because things happen at these limits that we don't really know about. In fact, there was some quote, I forget what it was. I should have put this on here, but there was like the CEO of IBM in like the 1960s. He was like, you know, by the 20th or by the year 2000, like, you know, maybe like 5 people will have like a home computer. So it was like, you know, okay, that's extrapolating 50 years out, but you can see like how far off some of our predictions can be if we're trying to extrapolate something way far into the future. Another thing that went wrong was our underlying assumption. Okay, so at the very start, I said, let's assume this linear relationship, but it doesn't take, whoops, going back, it doesn't take like a very like educated eye to really look at this and say that this is not quite a line. It's more of a curve, right? It looks like a banana. So a banana has that natural curve. Okay, so we'll talk more about this. I wanted to add a quote here from George Box, who's a famous statistician, which you may have even heard of, which is, all models are wrong, but some are useful. So this quote, what he means by this quote is that you can assume all you want, but there's always going to be some case that like is an exception to whatever you've assumed for your model. So the only case where a model would be perfect is if you had all of the data, or it was something that was perfectly predictable, in which case you don't really need a statistical model in the first place. Now, this some are useful. This is the takeaway I would get from this quote, which is that basically we're never going to do a perfect job, but depending on our expertise, we can do a better job than in some cases. So using this graph here as motivation, we can say, let's do better. Okay, this model is useful in some regard, but we can obviously do better. Okay, so here's a different approach. If you remember from intro algebra, quadratics. Okay, so you remember there's this little extra like curve. Okay, like a smiley face is a quadratic function. So take 2, we're going to assume a quadratic relationship. So now this is what our thing looks like, our relationship. We added this this quadratic term, and we can apply a similar procedure. I'm kind of like skipping over this. It's actually very easy to do mathematically or with a computer if you know what you're doing to fit this, even though it might seem like some arcane magic. It's pretty simple to do. So we're just going to take that for granted that we can do this. But here would be the curve. And if I plot it, let's compare. On the left, I do my line, and on the right, I have my quadratic fit. Okay, so it's looking better, right? It's looking much better. It has this little curve at the end. If we want to make a prediction at 550, it's about where my guess would have been. But it's still not perfect. Okay, so we can see, you know, it's not capturing some of these features at the top. And there's actually, you can see a hint of a big problem toward the end here. So when you're thinking quadratic, you're thinking smiley face, right? And that's what we get. Okay, so now instead of getting, what was it, like -10 for the miles per gallon, we're getting an increased miles per gallon. Okay, so this is the other danger, like this is just the general danger with extrapolation, that this is obviously not going to work when we're too far out of sample. Now, in any case, let me go back to that slide. In any case, our assumptions were not really fully valid. Okay, so the linear model back here, this wasn't really valid. This wasn't really valid either. Now the neural network approach would basically be to come up with some sort of model that was flexible enough that it is able to handle this type of procedure or this type of data, and hopefully it wouldn't like overfit it. The spline, which I showed like way at the beginning, that would probably be a pretty good model for this. We can kind of expect, like if you just want to look at this from a more bird's eye standpoint, we would say we probably expect the weight to decrease the miles per gallon. So for example, if we had a model that had like a dip here or it like went up, that doesn't really make much sense, right? We also expect it to be always decreasing. So the fact that this is happening, that's not very good. And we also expect it to not be negative. Okay, so any model that we hypothesize should encompass those underlying like facts about this relationship. So as long as the neural network, for example, satisfied those, it would do decent. But neural network is overkill for this type of procedure. This is just illustrative. So I made this slide here, which is think smarter, not harder, because we don't want to just like throw the kitchen sink at this problem. What I'm doing here is I'm showing a panel. Here is a data set. So if we look at this data set, there's what, like 10 points. If you look at the right panel, this is not the exact same data set. I think what I did is I changed like one of the Y values by like 0.01 or something. Now, what you can see is the linear regression fit, it didn't change like at all. But essentially, if we think back to that car thing, I just added on a quadratic term. What if we kept doing that at a third order term, at a fourth order term, all the way up to an eighth order term, or even higher? There's nothing stopping you from doing that, but this is a situation you get into. You now have a function that perfectly goes through all of the points you have, but there's no way that this is the truth. This is not the true underlying model. And for example, like, why would there ever be a predicted value that was like way down here if you're plugging 1.5 into this function? So you can see what happens is when the slightly perturbed data, look at how wild the shape has changed. Okay, so this is something we call model robustness. So if a model is changing this much with a very slight perturbation of the data, that's not a very good model to use. I'm not going to talk about this, but you might be interested in this. This is something called a ridge penalty, which adds a penalty term, which essentially penalizes for having too many terms that are unnecessary. And we can see that this actually does a fairly decent job, and it's not destroyed by the slight perturbation. Okay, so I need to speed this up a little bit. In the world of big data, we're going to have more than one variable, right? So all of those examples I just gave you, there's just the one variable, which was weight. So it's first off, far more difficult to visualize. So think about the 2D scatter plot, which I showed. You can't actually visualize data that way in like 5 dimensions. Okay, the best you can do is 3, in which case you have some like rotating type of computer object. If you want to do anything more than 3D, you need some very special tools, which is, it's more like a continuation of the data set, making it in a way you can visualize it. It's not really the original data set. One thing we should consider is that some of these variables, are they even useful? So let's just imagine a hypothetical example. What if car color was included in the data set? Do we really think that car color should change its miles per gallon, right? If you do a paint job on a car, is the miles per gallon going to change? Probably not. But imagine that there's a column that has car color. right? And you have someone who doesn't really know what they're doing and they plug this into a model. It's probably not going to hurt the model too much. You'll probably just get a coefficient that's like, okay, card color doesn't really do much, but it's adding this unnecessary thing, which is going to hurt the model overall. Sometimes this can actually cause a bigger problem than you might think. Okay, so coming back to a Gaussian process, which approaches this from a completely different perspective, what the GP does is it determines if a data point is close, depending on this thing called a kernel function. And what the kernel function does is it determines the underlying properties of the function. So in contrast with like the linear regression model, where it was like step 1, I'm going to assume a line, or step 2, I'm going to assume a quadratic curve. The Gaussian process takes a completely different approach, which instead assumes different properties of the function. So you could decide, is the function linear? Gaussian process actually handles that. You might want to understand, is the function continuous? Does the function have some sort of repeating patterns? Does the function have to be super smooth, or can it wiggle? Or can it be jagged even? Is there some combination of these things? And there's even more. In addition, the Gaussian process will provide full probabilistic properties. So what that means is you might be interested in like, well, how much are my future predictions going to vary? Or what is the probability that my prediction would be like above a certain value or below a certain value? Gaussian process will do this. So the mathematical details of this are pretty difficult. So if you want to tackle this at like a high level, you would probably need to like know some PhD level math to be able to handle it. But if you wanted to understand the basics and apply it, it's actually not that hard. So essentially, these are the types of things we're trying to think about, and we want to apply this idea to our data and understand it. So I'm going to skip over this slide, but I just wanted to, anyone who is mathy and wants to look at this, this is the definition. The multivariate normal, the normal distribution you think is this bell curve. So the multivariate normal, you have this multidimensional like bell curve. And that's actually all this is assuming. So what you do is you specify these two things, the mean function, the covariance kernel, which I talked about on the last slide, and boom, you have a Gaussian process. It turns out that for prediction, the mean function doesn't actually really even matter that much. It's the kernel that decides the underlying properties of this function. So if we want to understand what we mean in the first place by random function, we want to think about randomness like flipping a coin. Okay, so prior to the experiment, the outcome is unknown. So when we flip the coin, you get heads or tails. So that's called a realization. Now the experiment though, that's the actual process of flipping the coin. Or you can say prior to the coin being flipped, it's like, hey, Bob, I'm going to flip this coin, right? Well, Bob doesn't know if it's going to be heads or tails until you actually flip it. But we can talk about probabilistic properties of the coin flip, right? There's, assuming the coin is fair, there's a 50-50 shot, it will be heads or tails. So that's talking about the probabilistic properties. The realization is the actual outcome. So, right, we flip it, boom, it's heads. So you would have like a heads over here, or flip it and boom, it's tails. So you would have a tails. So essentially you would expect in the long run, if it's a fair coin, to have an even number of heads and tails, just to understand that a little bit better. So the randomness and statistical models, kind of comparing the three different approaches. In coin flipping, this is the phenomenon. The model is that the probability of heads is 0.5, or the probability, and the probability of tails is 0.5. This completely specifies the model, and then the realization, it's either a heads or a tails. Now, if we're going back to linear regression, the randomness is placed on this error. Okay, so we have to assume some sort of like model for this error. For example, it could even be a coin flip error if we really wanted. But we usually do some stuff with the data to try to understand what this error actually follows and fit an appropriate model to it. This then is deterministic. So if we're thinking about what is the realization of a linear regression model, well, this is fixed, okay? But this is some sort of like there's some uncertainty involved with this error. So what we can think about, even thinking about that car example, all of those data points were realizations, and the outputs were all of the y-axis values for different inputs. So those dots represented the realizations in the scatter plot. Now, a Gaussian process is a totally different story. It's not a bunch of dots. It's actually the entire function. Okay, so the line would be like a random line, or you could have a random curve, or maybe a random wiggly curve. Okay, so I'll show some examples of that in a second. I just want to refresh first, if we're looking at this, which one is correct, linear regression or a Gaussian process? Just real quick, neither is correct, okay? So remember this quote, all models are wrong, but some are useful. So would a Gaussian process do better than linear regression here? Probably, but there's another model out there that's probably doing better in this specific data set than a Gaussian process. Okay, so I'm not trying to say like this is the very best thing ever. I just want to introduce you to this and show you kind of the insight into this type of modeling problem. Okay, I can skip this. I just wanted to explain what the modeling, what the randomness portion looks like if we're trying to assume a linear model with linear regression. Okay, so let's say that this is the model we assume. So we don't have any data, but we're just going to pretend that this is the actual process that generated that car data. Okay. So what ends up happening is this error, this needs to be like randomly generated. Okay. So you could even flip coins in some sense to generate some random data. But this is what happens. I just generated like 4 points of data. So essentially what happens is from the simulation standpoint, you plug in the different weights. So like this has a weight of 3000, this gets plugged in, then you simulate an error and you add it to whatever this line is. So you can see they're close to the line, but not quite on the line because of that error. If I generate some more points, you see that this is now what it's looking like. So these are lots and lots of realizations. They're deviating from the line because of this error. Okay, we don't expect the weight versus miles per gallon to fully fall on this line because there's other things we can't consider. What the Gaussian process does, like I just mentioned, it samples an entire function. So rather than getting a point or a bunch of points, you get an entire path. Okay, so this panel right here, I took this from a really awesome paper, automatic model construction with Gaussian processes. But this blue line, this is one function that is sampled. This red line, this is one function that is sampled. And this is when we assumed this specific kernel, which is called the squared exponential kernel. So essentially from top to bottom, we say, let's just assume this squared exponential kernel. This assumes that the function is going to look really smooth. It's allowed to wiggle a little bit, but this is what one specific realization would look like. This is supposed to be periodic, so you should see some sort of repeating pattern. And you can see that that is happening here. The linear, you can see a similar thing. So by specifying this kernel, it produces lines. So as a competitive method, I just wanted to show this off. There's not a lot of details posted about this yet because it's very, very recent. But here's me and here's 2 other people I worked with. This is my old advisor from UCSB, and this was, she's actually a student of mine when I was there because I was TAing some classes. She's a graduating PhD student there now. And we actually won this mortality forecasting competition. And this is like a technically international competition. So you can see these people, I think, were from Purdue, and this is some practicing actuary somewhere. But we primarily used the Gaussian process and ended up winning this contest, which I thought was really cool. In a separate mortality modeling example, just to kind of show this off, we were able to show that you can see that this is a little bit old. This paper was from 2018. The red is the CDC data. So these are mortality improvement rates. So you can think about mortality as basically like, how often are individuals passing away? So before it was assumed that like, well, actually like in the Stone Age, like I guess the Stone Age when it comes to like mathematics or actuarial science, which is like insurance math, people assumed that mortality rates were just constant over time. But as we've kind of learned, like people are getting smarter, healthier eating habits, stuff like that. Mortality rates are actually improving over time. Okay, and that's what a lot of these pictures seem to imply. Now we applied our model and we found that there was actually for a certain age group that mortality rates were decreasing for certain age groups. And this was kind of dismissed by a lot of researchers. And in fact, here's the MP 2015, which is some like actuarial standard. And when we applied their model, it was actually forced to be positive. This model didn't even allow for negative mortality improvement rates. When the actual data came out, it actually very closely aligned with what our model showed. Okay, and it's a sad thing, but the mortality improvement rate being negative here means that for this age group, it's more likely for individuals to die as the calendar year is passing onward. And this has to do with something called deaths of despair, which is like a certain generation, like like the opiate epidemic and stuff like that that's happening. So I could go on about this, but I'll move on forward here. This one I just want to go over very quickly. This is a data set which is average atmospheric CO2 concentrations. Each point represents a data set. The line is just a connect the dots type thing. This is from 1958 to 1961, so just a snapshot. But you can see there's a lot of things going on. So there's an increasing trend. There's also this cyclic pattern, which is probably due to like monthly observations. So in certain months of the year, there's more or less CO2 concentration. But essentially, this is from a really good book, Gaussian Processes for Machine Learning. And what it does is it decomposes this as a Gaussian process of 4 different kernels. Okay, so I'm just going to go over this very quickly, but there's a long-term rising trend. There's a yearly decaying periodicity, so that's that cycle. There's small medium-term irregularities. So there's some sort of variation that happens, but it's over the medium term. And then there's this just pure noise term. Okay, so this would be the final covariance kernel by adding these all together. And this is what the prediction looks like. So the black dots here you can see are the actual data points. The orange is what the model predicts. In the blue is this thing that's called an uncertainty band. So this is, I think it's like a 95% confidence interval. This is saying that with 95% confidence, the atmospheric CO2 will be within these bands. The orange is the actual full prediction of this. So if you just went out in 2020, you could pick the prediction and, there you go. Remember what we said about extrapolation. I would not recommend going out that far, but the uncertainty bands compensate a little bit for that. Okay, so we can see the uncertainty bands increase as we extrapolate further out. So super resolution was the thing that I really wanted to focus on. I know I'm running out of time. I want time for questions. Super resolution, what this does is this reconstructs high resolution images from low resolution images. So a lot of techniques you may have heard of, there's this thing called bicubic interpolation. All that does is it kind of smooths out noise in an image. So our idea was to continue this work, which was very well done. They used Gaussian processes, but they used one single kernel. So kind of like compared to that work that I just talked about, where let's try a bunch of different kernels. Well, those were educated choices, but we're going to try different kernels to see how well we can do in this process of restoring image details. So here's the test image. This is the ground truth. So this is, if you're familiar with pixels, it's 192 by 192 pixels. Now, we're not supposed to know this. This is the ground truth. What we did is we shrunk it by a factor of 4. And what we're going to do is we're going to try to train a model to this image. It's not allowed to know this ground truth whatsoever, but the goal is to restore the ground truth as well as possible. So this is that smoothing method that I talked about, which is bicubic interpolation. And it doesn't even really look that much cleaner than the low resolution image. So here's what happens if we try different kernels, just to kind of look at this. So this is a little bit hard to see. On the next picture, I'm going to show the zoomed in details, which is right here. So here's the linear kernel, which is just like a linear model. Here is a very smooth kernel. Here's a non-smooth kernel, and here's a periodic kernel. Now, one of the things that we did this just to kind of see, well, what happens when we change the kernels? And what you can actually see is this non-smooth kernel. When you're thinking non-smooth, you want to think like jagged, like it's not a very like smooth function. It's very rough. It actually restores the details on these stairs very well. Okay, and this is something we had not anticipated before we started this experiment, but it kind of makes sense because these are very jagged jumps, right? These smoother kernels, they're trying to like smooth out the white in the brown, but this says, hey, I'm allowed to have these big jagged like changes. So this kernel actually allows for that. Another thing we saw that was really interesting was the periodic kernel kept showing up as doing well. So ignore this green stuff. It's just there's one little small problem in the fitting. But what the periodic kernel does is there's actually periodicity on these staircases. Okay, so that with the spokes, right, there's a repeating pattern. With these stairs, there's a repeating pattern. So we were also incredibly surprised to see this doing well. Now, what we did is we applied this automatic kernel search algorithm, by the way, like 2 more minutes here, to come up with a kernel. And this is what the kernel came up with. So it kind of verified some of the things that we mentioned before. It has this periodic component. This is also like a not very smooth kernel. This is something called the Mattern 3 halves kernel. And this is what ended up happening, okay? So here was the low resolution image. Here was the ground truth. Just to recap, the model had no idea what the ground truth looked like. It was trying to restore this. The bicubic interpolation, which is like a very common method, it's not great at restoring high frequency details, but it's used because it's quick and easy. And here's what ours did. Okay, so it used this low resolution image and restored this image to look like this. And if we want to compare some of the details, here was the best kernel that we got. This is zoomed in pretty far, so you can't like see it perfectly, but you can see, in fact, it's probably zoomed in too far. I didn't even think about this. These aren't designed to actually be blown up like this, but you can see that it's restoring some of the details on these spokes. Okay, much better than the bicubic interpolation, which kind of just like smooths it out. And it's also able to restore some of these details on the stairs here, better than the bicubic interpolation. You can see like the edge of the stairs and stuff. So this honestly probably gives a little bit of a better view if you can see it. If you just look at some of the stairs here, this looks a little smudged. This looks pretty clean compared to the ground truth. Same with the spokes up here, it looks better. This is how it's supposed to be viewed because these are the actual sizes of the images. When you blow it up, it might actually make it look not as good. Okay, but that's all I had to say. So thanks everyone for your time. And then these are the 2 different works that I'm talking about here. I'm actually working, so Charles is a master's student of mine that we worked on this together, and we're actually going to try to publish this into something, into a paper, because I thought it was so cool. But yeah, this is my talk, and I'm open for questions if anyone has any.
Great, thank you very much. There's a great question here about the how random your background is. So But I will actually turn the time over to you all. If anybody wants to jump in and ask a question.
So I have a question. My research is on protein structure, and I use X-ray crystallography, and we often have issues with limits of resolution. And so I was wondering, have there been applications with this type of fitting when you start looking at, diffraction data that's going to have, this aspect of almost like a grading or a lattice that the data is filtered through?
Yeah, so I don't know too much about that specifically, but I do know that this is used a lot in medical imaging. So like I think it's used in like MRIs and stuff like that. The other thing that it's used in is what's the term for that? Laparoscopic surgery, where like you put in a little camera and like the surgeon is supposed to like kind of work with a zoomed in version and like inside of someone. This is used in that. So maybe not specifically this Gaussian process version, but super resolution is used in those applications. But technically you could apply a Gaussian process to it. It might do a pretty good job.
Now there's a question in the chat. Is spreadsheet random number actually random? Would it be useful for sampling?
Are you talking about just like, so you're talking about like in Excel, right? Like random.
I'm going to ask David to unmute himself and clarify his question.
I think I know what David's asking. Maybe he doesn't have a microphone. So technically any sort of like computer generated randomness is not technically random in the sense that we would expect it. It's something that's called pseudo-random. But it's like the best that you have, and like to the unaided eye, you can't really tell. If you wanted to be like perfectly random, you would technically want to like shake some balls up in a box or like flip some coins. There's actually a site called random.org, which generates random numbers from like atmospheric noise. So in that sense, it's like more random. But I don't see any like real problem with like spreadsheet random number generation, or just like if you were to just use like some computer program and do like random integer or something and get some random numbers. Technically, it uses the computer's clock, and that's why it's called pseudo-random, because it's not fully random. But yeah, like I said, to the unaided eye, you can't really tell, and it's good enough for most applications.
And we've got another question in the chat. Do Gaussian processes in the industry also utilize multiple kernels, or do most just stick to one kernel? And does it depend on the domain? And then I kind of want to add a question onto that. Do folks tend to fall in love with like their favorite kernel or their favorite combination of kernels?
Okay, these are all really good questions. I love Alejandro's question because I'm trying to almost send out a PSA of don't use just one kernel. In fact, like this work right here, which is the first paper we looked at, they use the squared exponential kernel, or it has a bunch of different names, the radial basis function kernel, the Gaussian kernel, but it's so commonly used just because everyone else uses it. And it's not the best. And in fact, I don't think a lot of people realize that it doesn't have like, it's not applicable in a lot of settings. There's much better choices. So that was actually one of the purposes of this kernel, or sorry, this thesis, was to illustrate that idea. Like, hey, the kernel, which like everyone just uses this one, if we change it up, it does some drastic changes to the output. But in industry, yeah, people just tend to use the squared exponential kernel. Some people also use the linear kernel, but I would say like probably 95% of what I see, they use one or two of those. In the papers, they'll also usually start it off by with like saying something like, the Gaussian process is defined by its kernel, which like strongly influences the blah, blah, blah. And then the next sentence is like, for this work, we use the squared exponential kernel, and then just like leaves it at that. So yeah, does it depend on the domain? I think in terms of like industry domain, that's a good question. I haven't really seen too much of a trend there. It's usually either one of those two, like I said, squared exponential or linear. But there are actually very complicated types of kernels you can use. So like, for example, if you're trying to do, let's say natural language processing, where like your input rather than like numbers are actually like words or phrases, you obviously can't like subtract two words and get a measure of like how close those words are. You need more specialized kernels, and those types of things exist. So they would be called, they're variations on this thing called a convolutional kernel. So that's one spot where in a different domain, you actually have to use a different kernel. In terms of favorite kernels, yeah, I'm, in fact, I think a lot of people are kind of partial to using this Mattern 3 halves, or actually the Mattern 5 halves, because it's a lot of people say that this RBF kernel, which I said was smooth, that's the one I was talking about, is super popular. It's like too smooth. Like it's unrealistic to expect the output of a function to be this smooth. So I like the Mattern one because it's not too heavy of a restriction. But I would say, in the perfect world, everyone is going to pick their own kernel that's good for the job, or do some sort of model selection to find one.
I think we've got, maybe this will be our last question for this evening, unless there are more. In the chat, would it be safe to say that using a spline type polynomial model of an order greater than 1 is almost never a good idea for extrapolation?
Yeah. It's almost never a good idea to extrapolate in general. You always have to use like, you always have to take extrapolation with a grain of salt, and you always have to like kind of apply some expert knowledge or expert opinion, at least in my opinion, to like the domain to understand if this even makes sense. But yeah, in general, like what Matthew is kind of saying is, if we go like way back to the smiley face, if we extrapolate too far, this thing just goes like way off, right? If we're trying to understand a car whose pounds are like 20,000, the miles per gallon is probably going to be like in the hundreds, and that's not realistic at all. So it's definitely more dangerous to extrapolate if your polynomial is higher degree like this, but it's dangerous to extrapolate in general. Like this, there's also problems here, obviously. This is why, I guess if you're not really sure, yeah, I would use a lower order polynomial, but yeah, I guess I could ramble and talk about that for a while, but to answer your question more concisely, I would say it's definitely not a good idea to extrapolate too far with a high order polynomial. Otherwise, you get into this type of situation.
All right, and then there is one more. In general, what is the runtime complexity of the Gaussian process?
So the runtime complexity, it's order of n cubed, where n cubed is the number of data points. So if you know what that means, you're probably cringing at that statement, because anything that has that long of a runtime is not good in a lot of settings. Like it's just takes too long. But there are some ways to speed it up. I most of the data sets that I work with are small enough that it's not an issue. But that sort of thing is out there, in which case it becomes like n squared times something else, which is depending on what method you use, that something else can vary.
All right, so the questions keep coming. So we've got a very engaged audience tonight. This is wonderful. So in the world of big data, is it rare to escape those extrapolation worries? For example, a model might not even worry about cars over 100,000 pounds because that's unreasonable.
I'm not sure I fully understand the question. Yeah, it's I wouldn't care about a car over 100,000 pounds. The model shouldn't either because there's no data there. I guess it depends on the extent of your extrapolation, because like, is this okay to extrapolate to 5,500? Well, if you create a really good model, yeah, probably. I would say that if you're extrapolating, the uncertainty is really, really important. So like if we go to that case of the Gaussian process, this doesn't just provide like a point prediction, but it has these bands, which is informing you that we're getting less and less sure as we extrapolate further out. So I would say that if you are planning on extrapolating, something that is able to handle this would be desirable. So you can see how unsure a certain model is. But basically in the world of big data, I guess to add to that comment, which you said, if we have the data, we can fit to it. But you also need like a lot of data to kind of understand what's going on in that spot. So like if we go back to the car example, and let's just say like I had one lone point out here, which was like 7,010. It's going to change the fit to some degree, but these are still going to, there's a lot of points here. So that's still going to influence the fit. This point would be influential, but it's still going to, regardless, you can tell that this is a bad model choice because it doesn't matter. It's quadratic. So like in the very, very long run, when you plug in that 100,000 pounds, it's going to be way too high or way too low. You can always go further. That was a little bit like scatterbrained just because I wasn't sure exactly what you were asking, but hopefully that helped clarify.
I think with that, we'll call it an evening. Thank you so much, Jimmy Risk, for coming and presenting tonight. It was great. And thank you all again for participating. We had some good participation. Have a great night, and hopefully we'll see you at the next Science on Tap.